Good morning, good afternoon, everyone. My name is Ben Cohen, and I'm a Senior Marketing Engineer with BAC. I'm joined here by Steve Klein, who's the National Sales Manager for Commercial HVAC at BAC, and he's going to be answering questions with me during the Q&A session. Regarding Q&A, you can enter questions into the chat on the screen. Feel free to ask questions. We're going to try to answer as many as we can at the end of the presentation, and I'll repeat this at the end. But for those of you whose questions we can't answer or don't have time to answer, we'll reach out privately and get back to you with communication. But before getting started, this is a very significant day, and I'd like to take a moment to honor those that serve their country as well as those that have sacrificed their lives. So please join me in a moment of silence to honor those men and women. Okay, thank you. So, welcome to the webinar. It's titled New and Innovative Ways to Reduce HVAC Operating Costs, and it's really specifically related to water-cooled HVAC systems. We hope that you find the session very valuable, and most importantly, we hope that you can actually take this information and apply it to your designs and your building operation as well. So let's start with an overview of this presentation. First, I'm going to give an overview of the HVAC system and really compare water-cooled systems to air-cooled systems. And I'm going to explain why water-cooled systems can really offer the lowest total cost of ownership for building designs. Then, next I'm going to discuss methods of design that can increase energy efficiency by nearly 50%. They can reduce system costs by 33% and greatly increase equipment lifespan and system reliability. And finally, I'm going to review some new and exciting technologies that have been introduced recently, and that includes more advanced heat transfer technologies. There's one in particular that's a Counterflow technology that actually increases thermal performance by 30% over traditional Counterflow designs. I'm going to talk about more reliable and energy-efficient drives that can reduce energy consumption by 10%, and materials of construction that can increase system reliability and can also extend the life of cooling towers as well. So with that, let's start with an overview of the HVAC system. Now, this schematic that's shown on the screen, it represents a very typical building with a chilled water system. This system includes a chiller, but the same general layout's going to exist for a heat pump system as well, or other systems with those components replacing the chiller. And the purpose of the chilled water system is really strictly to remove heat from the building and cool the required interior space. From a systems perspective, there are three main subsystems that complete the total HVAC system. Okay, so first you have the air conditioning and distribution system, which includes the air handlers. It conditions the outside air, or the recirculated air, and distributes it to the space that's being cooled or heated in the building. Next, we have a hot water system, and that heats the air that's supplied to the space. And then we have the chilled water system, which as I mentioned earlier, it collects heat from the building and it rejects it into the outside atmosphere, into the outside air. So when you consider the air distribution system and the chilled water systems working together, the air distribution system is essentially supplying the chilled water system with the heat, and then the chilled water system is rejecting that heat to the outside atmosphere. So there are two types of chilled water systems that can generally be used. You have air-cooled and water-cooled systems. Air-cooled systems include an air-cooled chiller that rejects heat to the outside air through outdoor condensing units. This heat is typically rejected through sensible cooling and it depends on the outdoor ambient dry bulb temperature, and this is very important that it cools to the dry bulb temperature. Now, water-cooled systems, on the other hand, have a condenser water loop that includes a water-cooled chiller and a condenser pump, and then heat's rejected from the cooling tower through evaporative cooling, which depends on the outdoor ambient wet bulb temperature instead of the dry bulb temperature. Now, as I mentioned before about dry bulb versus wet bulb, the difference between these types of temperatures or these types of measurements is very significant. The ambient dry bulb temperature is always going to be higher than the wet bulb temperature. So an air-cooled system typically requires a larger footprint and higher energy consumption than water-cooled systems. Now, while air-cooled systems don't consume water on site, water usage is still pretty significant at the power plant because water is required to generate all the electricity. And water is essentially a renewable resource. Now, since water-cooled systems depend on the wet bulb temperature, which, again, it can be several degrees lower than the dry bulb temperature, the outdoor footprint of the equipment is going to be much smaller, and energy usage is going to be much lower than on air-cooled systems. So I just want to expand on this point for a moment. Here's a typical 500-ton system. An air-cooled system, typically, this particular air-cooled system costs about $132,000 in energy usage. And again, no water is consumed on site with the air-cooled system. Now, if we compare this to a water-cooled system, which costs $70,000 in electricity and $18,000 in water costs, and the water costs include evaporation, blowdown, and water treatment as well, that's a total of $88,000. This is $44,000 less per year in operating costs, and that basically brings down your energy consumption by 48%, and it offers 33% savings in annual operating costs. And remember, these are annual operating costs. So that said, let's actually expand this to lifetime costs. A water-cooled system, well, this chart actually shows the trajectory of air-cooled versus water-cooled systems. So a water-cooled system may initially cost $54,000 more than an air-cooled system, but it actually can last twice as long as the lifespan of an air-cooled system. Now, the water-cooled system can offer a payback in just over 1 year. And over a 20-year period, a water-cooled system saves more than $800,000 over an air-cooled system. Okay? For this building system, a water-cooled system really shows a clear advantage in total cost of ownership over an air-cooled system. Now, I know this has been said many times, but building owners definitely are becoming much more energy conscious, and they're becoming more focused on sustainability. Everyone recognizes that sustainability does go hand in hand with growing business by lowering operating costs that better reflect shrinking maintenance budgets, really. Owners and property managers are also trying to continue to meet the general public's expectation for low energy usage as well. And also all levels of government, so state, local, federal, they're all enforcing more stringent energy requirements. And our industry, the HVAC industry, is driving higher efficiencies through energy codes like ASHRAE 90.1 and like California Title 24. So all cooling tower manufacturers have really stepped it up over the years and continue to educate engineers, owners, contractors, architects, really all stakeholders in building design and construction, and educating them on design and operating strategies. And we've also introduced new technologies that support these strategies. And I mentioned ASHRAE 90.1 in the previous slide. It's been the dominant energy code pretty much across the country. It's been very, very widely adopted. From 2010 to 2013, the minimum energy requirements for axial fan units increased from 38.2 GPM per horsepower to 40.2 GPM per horsepower. And this represents a 5% increase, about a 5% increase in energy requirements since the 2010 code release. Now, centrifugal fan cooling towers, which use about twice the energy of axial fan towers, haven't increased in minimum efficiency requirements. However, there are now limitations in place that require the same rating as axial fan units for centrifugal fan units above a certain tonnage. And as I said, this is what the market demands. So we can expect this trend of increasing energy efficiency requirements, and that's going to continue. That's not going to slow down. So now we've covered the HVAC system basics and current energy trends. So I want to discuss some design methods that can be used to increase energy efficiency, reduce costs, and extend the life of your equipment. The first design method that I want to review is designing for a lower condenser water approach. Now, when you design a system with a water-cooled chiller, it's very important to understand how operating costs are going to contribute to the total cost of ownership. It's a very significant cost of the entire system. So since the chiller consumes by far the greatest amount of energy in a water-cooled system, any increase you can provide in chiller efficiency can really offer the greatest return for your investment. And just to highlight this, a water-cooled chiller uses about 2.5% less energy for each degree below 85 degrees that enters the chiller. So now I'm going to define approach and explain how you can achieve greater efficiency. So nominal design conditions for the condenser water loop in general, 95 degrees back into the cooling tower and back to the condenser or chiller, 85 degrees leaving the tower and going to the chiller, and a 78-degree outdoor ambient wet bulb temperature. So these are very typical conditions for many regions in the U.S., and that includes the Northeast. Again, it's 95 into the tower, 85 out of the tower, 78-degree wet bulb. Typical for the Northeast. In certain regions in the country, let's say Miami, it may be more like 79 or 80-degree wet bulb, but these are pretty typical design conditions. Now, the range is the temperature difference between the water entering and leaving the cooling tower. So in this particular case, it's a 10-degree range. The approach is the difference between the leaving water temperature and the outdoor ambient air wet bulb temperature. I just want to reiterate again, the cooling tower cools to the wet bulb temperature, which is generally lower than the dry bulb temperature, which is what gives evaporative cooling its efficiencies. So the 7-degree approach, again, difference between the leaving water temperature and the wet bulb. So the wet bulb is really the temperature that you're trying to cool that temperature down to. So earlier I focused on wet bulb temperature. Since the design wet bulb temperature is so much lower than the dry bulb. When it comes down to cooling tower and chiller optimization, the approach is absolutely critical. Okay? So let's consider a 500-ton system design, assuming 1,500 GPM, which is 3 GPM per ton, through the condenser water loop. The range, which again is the difference between the water entering and leaving the tower, is determined by the size of the heat load removed from the building. So for each of the 3 conditions listed on the screen, a 500 nominal ton cooling tower can do this required duty at these design conditions. However, the last condition, which I highlighted here, shows it really offers the greatest system energy savings since it has a closer approach, which again is the difference between the cold water temperature leaving the tower and the ambient wet bulb temperature. A closer approach is going to reduce the amount of chiller work that's required. So what does that mean? It means that you can either select a smaller chiller or you can run a larger chiller using less energy. So by selecting a higher capacity cooling tower, you really have a great opportunity to reduce this chiller work and cut down on total lifetime costs. Now, when you're optimizing the system to reduce total cost of ownership, always make sure you consider the first cost of the equipment. So that includes the cooling tower, the chiller, the condenser pump and piping, along with associated energy costs. Now, there's not a single control strategy. It's not really a one-size-fits-all strategy that's optimal for every single building. However, many cooling tower representatives do specialize on water-cooled HVAC systems, and they can work with you to optimize systems to meet your specific needs. In the long run, it is definitely worth spending extra time on system optimization because you do want to reduce these energy costs and the total cost of ownership. The optimization is a win-win for all parties involved because it does reduce life cycle costs for the owner. It reduces energy costs. It can even lower sound levels since a cooling tower that has more heat transfer surface area typically requires lower fan speeds. And then also for those systems that can benefit from operating in a water side economizer mode, the system can actually run longer without operating the chiller if you have a larger tower. And, you know, I've just been talking about optimizing the system from a cost of ownership perspective, but there's an even greater opportunity to reduce energy costs by producing even colder chilled water. Now I've reviewed system optimization. Let's move on to the next design method, which is selecting cooling towers with extremely high energy efficiency. Now, BAC defines extreme efficiency towers as having at least 2 times the ASHRAE 90.1 2013 energy rating. Now, cooling tower manufacturers in general, most manufacturers now offer extreme efficiency models with a very broad range of fan motor horsepower, and this actually makes the selection process very, very easy because by simply selecting a cooling tower with more surface area, which is generally going to be a tower that has more efficient heat transfer surface, or it can be a taller unit or one with a larger footprint, it's very easy to evaluate and identify which tower is going to give you higher efficiency. And because of the fan laws, you can really achieve some really great energy reductions since energy usage equals the fan speed to the third power. So once you enter your conditions into the manufacturer's selection software, you can compare the ASHRAE 90.1 energy ratings along with the payback to select a cooling tower that offers the lowest total cost of ownership or that meets your needs. And as an example, let's again look at a 500-ton system. The model with the lowest first cost can do the required performance by using a 40 horsepower motor. However, by selecting a model that has a 20% higher first cost, you can achieve payback in just over 1 year. So this is a screen capture of BAC selection software, and just to give you an idea of how to select these towers. By evaluating energy ratings and different payback periods, owners can really save quite a bit of energy. In this particular selection, the third model listed offers half the horsepower as the lowest first cost model in just over a 1-year payback. And now compare this extreme efficiency cooling tower energy rating. It's 98.8 GPM per horsepower. Compare that to the model that has the lowest first cost, which is 47.5 GPM per horsepower. And you can see that the extreme efficiency cooling tower has twice the efficiency as the unit with the lowest first cost. Now, this energy reduction also lowers total cost of ownership, and it has a lower environmental impact since only half the energy is consumed. And I keep touting extreme efficiency towers, so I do want to show the numbers. This particular example demonstrates how the reduced operating costs of an extreme efficiency cooling tower can benefit the owner over the life of the cooling tower. So by looking at these bars, the blue bars represent first cost. You can see that the extreme efficiency model is really only slightly more expensive than the lowest first cost model. Now, while the lowest first cost model has a 40 horsepower motor, the extreme efficiency model has a 20 horsepower motor, which again is really offers half the operating costs. So at 12 cents per kilowatt, 2,500 equivalent full load hours in a year, the extreme efficiency model over a 20-year life of the unit can save $100,000 when you compare it to the unit with the lowest first cost. In general, the extreme efficiency cooling towers will, again, they can lower operating costs. They can offer a payback generally in less than 2 years, and they reduce energy by up to 75%. And then I mentioned it earlier in a previous design method, but since the fans in extreme efficiency towers are slower, since the tower is generally larger or more efficient, the fan can move slower, and you can reduce sound levels by as much as 5 decibels, which is pretty significant. These efficient models can also increase system reliability because there's going to be less wear on the mechanical moving components like your belts or your shivs or your gears. And finally, these extreme efficiency towers can actually contribute to energy and atmosphere credits for LEED certification. So we've now gone through methods to reduce energy usage and total cost of ownership. So now we're going to discuss a way that can really increase overall system reliability by closing the condenser water loop. Now, building owners spend a lot of money on these systems. They're very expensive, and owners want to, they expect to maintain peak performance for a very long time. By closing the condenser water loop, you're essentially protecting the chiller or heat pump from dirt and debris. And since the chiller consumes the most system energy, it really pays to protect the chiller from fouling, which can ultimately lead to some really big efficiency losses. To put this in perspective, or to really highlight the magnitude of fouling and what it can do, this is a picture of a typical heat exchanger before system operation. Now, without really cleaning the tubes, you can see what happens over time. This is the fouling that can occur, and it can really reduce your chiller or your system efficiency. So the question is, what can we do about it? As I mentioned earlier, we can close the condenser loop with a closed-circuit cooling tower. Now, a closed-circuit cooling tower, what it does is it actually isolates the condenser loop through a serpentine heat exchange coil. So this coil, it's shown on your screen to the left. This is placed inside of the closed-circuit cooling tower, and the tower recirculates water over the coil, and that's where the evaporative cooling occurs. Now, the process fluid inside the coil is transferring heat through sensible heat rejection, so that's not evaporating, but the evaporation that's occurring on the coil, that's what really enhances your heat transfer. Since the tower is recirculating the water over the serpentine coil, what's happening to all the dirt and debris that normally enters the system? Well, instead, it's being collected in the tower's collection basin. There's a strainer in the basin that prevents the dirt and debris from continuing to be recirculated. And the closed process loop that's basically contained within the coil prevents the dirt and debris from entering the rest of the HVAC system. So closing the condenser loop, it can eliminate oxygen corrosion and airborne dirt from the rest of the system, like I just discussed. And it can also eliminate the need for a secondary loop when a heat exchanger is used. Also, when you're operating a unit in harsh climates with harsh winters, you can prevent freezing and ice buildup, and you can even eliminate plume. By operating dry, you can also reduce water usage. Also, when you eliminate the heat exchanger, you can really simplify installation, and you can reduce your overall installation costs. Closed-circuit towers are also great for layout flexibility and simplifies installation. Open towers are always located at the highest point in the piping system in order to function properly and make sure that that the basins don't overflow. Closed-circuit cooling towers, since you have a pressurized process loop going through the coil, the closed-circuit tower can actually be placed at any point in the system, including at grade level, so it can really help out when flexibility is required for layout, depending on the job site requirements. Also, just one last thing that I want to mention that's not on the screen, for systems that benefit from high turndown levels, closed-circuit cooling towers can handle a very wide variation in system flow. Since we've reviewed cost-saving design methods, we went through the three that I wanted to discuss. Let's move on to technologies that can also reduce total cost of ownership. And we're first going to start with a new counterflow technology that can increase energy efficiency by up to 30% over conventional counterflow designs. Now, throughout the years, there have been different technologies for closed-circuit cooling towers that have been introduced to provide much greater thermal performance. However, before the 1990s, really the only packaged closed-circuit cooling towers that were available on the market just included a serpentine coil as the heat transfer surface. However, in the mid-90s, BAC actually introduced the first factory-assembled closed-circuit cooling tower, and that had both a serpentine coil and fill media. This crossflow design has really been the industry standard in thermal performance or efficiency, reliability, and accessibility for maintenance really ever since it was released. And I don't go into crossflow versus counterflow too much in this presentation, but one of the great benefits of the crossflow design is accessibility, because you have an area where you can access the collection basin, the distribution basins, and the drives, which are essential to unit operation. Now, while counterflow closed-circuit cooling towers are a bit more difficult to maintain because they don't have as much accessibility, they can still be very useful when replacing existing counterflow units, or when there may be certain layout restrictions and a crossflow unit isn't ideal for that particular situation. In 2015, BAC actually introduced a new heat transfer technology. It's only available for counterflow cooling towers or closed-circuit cooling towers. This design includes fill that's actually nested between coil rows, and it increases thermal efficiency over traditional counterflow closed-circuit designs by as much as 30%, while still offering dry performance for buildings that do benefit from operating dry during the winter. Now, again, the crossflow design, it's still more energy efficient. It offers a lower total cost of ownership than the counterflow design. But this particular counterflow design offers a benefit that's very similar to what Crossflow offers. This technology can actually reduce fouling by around 50%, since the majority of the evaporation occurs on the fill and not on the coil. And fill is much less expensive than the coil, and it's easier to access and to replace when necessary. Now, this will really allow you to operate the equipment at peak performance for a longer period of time. And again, as what's been the theme throughout this presentation, this is going to reduce your total cost of ownership. There's another feature that I wanted to highlight of this new counterflow design that helps reduce energy consumption over traditional closed-circuit cooling towers, and that's the optimized spray distribution system. BAC actually calls it the OPTISPRAYT distribution system. Now, by optimizing both the recirculating water flow, or the spray pattern, and the airflow, this design can achieve greater thermal performance than traditional designs, and it can actually do this with a smaller spray pump that can use up to 60% less energy. Now, since the spray pump runs throughout most of the year and it's always at full speed, this smaller pump size really minimizes the total unit energy that's used and reduces energy costs throughout the year, because the fan motor can actually be throttled by the VFD, whereas your pump's going to typically be running at full speed all year round. Now, because of the optimized spray and airflow, this technology also can reduce the amount of recirculating water in the system, so the falling water produces lower sound levels than traditional counterflow designs. And again, I just want to reiterate, Crossflow units still offer greater efficiency, access for maintainability and reliability because of the accessibility that you have. They do offer all those benefits over counterflow units. However, this advanced heat transfer technology and the new spray system really provide great benefits over traditional counterflow designs, and really do make great replacements, and again are excellent for situations where you need to save space. Now, I did spend time earlier discussing the extreme efficiency cooling towers, and I just really want to take the opportunity to reiterate it, particularly because you can combine the extreme efficiency tower selection with these other design strategies and these technologies. So, again, this energy savings is going to contribute to your to basically lower your total cost of ownership. And again, it can contribute to LEED energy and atmosphere credits, and also typical paybacks, again, less than 2 years. So on the right, you can see the cost savings between a model that has the lowest first cost with a 35 horsepower motor and an extreme efficiency model with 20 horsepower. And this analysis, or this evaluation, also includes pump horsepower savings as well. The extreme efficiency model, as you can see, it saves $126,000 over the life of the equipment. And this all adds up, and it's all these different design strategies and technologies add up and are very important to lowering your total cost of ownership. So now, let's talk about how new drive system technologies can lower energy usage by 10% and can really greatly improve reliability. Historically, and really traditionally, gear and belt drive systems, they've been used in factory-assembled cooling towers for years, and belt has really gained popularity and acceptance and has become easily the most common drive system in the market. Now, belt drive systems have definitely become more reliable over time, due in part to better system designs and better drive designs, and also because VFDs are used much more frequently than they used to. VFDs provide soft starts on the mechanical components. Belt systems are also much less expensive and much easier to replace than gears when gear systems go down. Gears still do have a place on some of the largest motors, for instance, on 100 horsepower applications, where it's a more practical solution at that particular size, but gears do have higher maintenance costs, and they have the potential for extended downtime. They also have greater environmental impact because of oil change requirements. So let's look at the costs of both the belt and gear drive system in terms of labor and materials. When you compare labor and materials, belts really are going to win every time. The material costs you can see here between belt and gear, it's really a wash. They're about the same. However, the maintenance is really where it shines. Belt drive maintenance can be really estimated about $300 a year versus gear maintenance of $900 a year. So when you look at the total cost, you can see that by having a belt drive system, that's going to have about half of the maintenance cost as gears. And you add this up over the years, and the cost savings are really going to add up. So even though belt does offer a lower total cost of ownership than gear, but with both belt and gear, there are still mechanical components. They're moving components, they're moving at varying speeds, and they're going to degrade over time. This degradation is going to introduce mechanical losses into the drive system. So that's where direct drive technology comes in and really shines. So previously, there have been challenges to using direct drive motors and cooling towers, particularly on larger cooling towers. With slower operating speeds, direct drive motors require much greater torque than induction motors that typically operate at about 1,800 RPM. Now, in the past, this really limited direct drive to motors at about 15 horsepower and smaller, which can be small for cooling towers. Now, however, there have been recent developments in technology that have made direct drive much more practical and much more cost-effective for factory-assembled cooling towers. Direct drive technology can now actually replace the traditional drives, both belt and gear, and it offers benefits that they weren't available before. There's far greater reliability than traditional drives. Since there aren't any couplings or shafts, direct drive completely eliminates misalignment issues on gears. And also, you definitely don't expect any coupling failures that can occur with gears because there aren't any couplings to fail. Instead, with the direct drive system, the fan is actually mounted directly to the motor shaft. The direct drive system, in general, requires maintenance once every 17,000 operating hours, and based on typical building operations, that's a 5 to 7 year maintenance interval. Maintenance is very, very easy also compared to both belt and gear. All you have to do is grease the motor bearings instead of performing messy oil changes, alignments, even with belts, replacing the belts. This is all expensive and time-consuming, and can really reduce your planned downtime. Since there aren't any mechanical losses as well, direct drive does allow for increased thermal performance, which this is great because it can either lower your fan horsepower or it can reduce the size of the tower that's even required on site. Since there aren't any mechanical losses or mechanical degradation that I just spoke about in the last slide, energy usage can actually be reduced by up to 10% versus traditional belt or gear drive systems. And then also, since this is operated by a VFD, direct drive systems are always going to be operated on a VFD. This is going to provide additional energy reduction throughout the year and is going to help qualify for energy rebates in many states. Another benefit, and I've talked about noise and sound levels in a couple of previous of the design methods. Noise reduction is very real with direct drive because noise from gear mesh can be completely eliminated by replacing gear with a direct drive system. Direct drive fan systems are really they're really an excellent choice for installations where reliability and energy usage are important, which is a lot of installations. Since there's a 5 to 7 year interval with direct drive fan systems for maintenance, this is a great option for buildings that have where there's been a reduction in maintenance budget or a loss of maintenance staff. If your tower falls short of required performance, let's say that there have been new heat loads that have been added to the building, more people, more equipment over time, the direct drive fan system can actually add enough thermal performance to ensure that the building can meet its required cooling capacity. Now, in addition to selecting a unit with a direct drive system, if you're going to replace an existing gear system, this could really be the perfect opportunity to replace it with a direct drive system. And then also, if you've had excessive vibration from wear and tear on the existing drive system, a direct drive system can be really an excellent solution for vibration reduction. Now, this chart can give you an idea of the overall savings that you can see or that you can expect from the direct drive fan system. Again, we're going to assume 2,500 full load hours, 12 cents per kilowatt, a $10 per kilowatt demand charge, and a 100 horsepower motor. So over a 20-year life of the tower with the 100 horsepower motor, an owner can save $119,000 over a unit with a traditional drive system. This is going to greatly reduce your tower's total cost of ownership, in addition to reduced maintenance hours and less downtime. Both the engineering community, along with owners, are really accepting direct drive technology as a more reliable and a more energy efficient method of fan control. And the picture on the screen, this is actually showing an issue of Consulting Specifying Engineer magazine that was published earlier this year. There's a very detailed article that highlight the benefits of an actual installation with direct drive cooling towers. And again, direct drive technology really offers a great opportunity to increase reliability and reduce energy usage. Feel free to read all about it in this case. It's very interesting and can really help you reduce your total cost of ownership. So now we're going to talk about one final new technology, which is more advanced materials of construction that can extend equipment life and reduce lifetime water usage. There are really three main areas of the unit that are most susceptible to accelerated corrosion. So these components are your basins. The basin on top of the unit, or the basins on top of the unit, are your distribution basins. The basin at the bottom of the unit, that's your cold water collection basin. When the cold water collection basin corrodes beyond repair, often it's actually more practical to replace the entire unit. Replacing the other panels is really not nearly as much of an issue as replacing the cold water basin panels. So protecting that cold water basin is absolutely critical to ensure the longevity of your equipment. The next areas that are susceptible to corrosion are any submerged components, so that would include supports and strainers. And then the areas that are least susceptible to corrosion are areas that aren't fully submerged in water, like casing panels and some structural members, but they are still vulnerable to corrosion. Traditionally, factory-assembled cooling towers have been constructed from either galvanized steel with a thermosetting hybrid polymer coating, that's a powder coating, or stainless steel. Now, galvanized steel offers the most basic level of corrosion protection. Then, by adding a thermosetting hybrid polymer, again, it's a powder coating, you're adding another layer of protection, and also you don't need to passivate a tower that's coated with a protective coating. Stainless steel does provide a much greater level of protection, but it does also add a lot more cost than a conventional galvanized tower. Stainless, or any material of construction that can provide higher corrosion protection than galvanized, it does offer the opportunity to save water, since you can increase the cycles of concentration in the water and still have a very long-lasting unit, or extend the life of your equipment. Over the last several years, more advanced and cost-effective materials have been developed that offer an alternative to stainless steel. For example, a polyurethane coating on the cold water basin can offer a huge jump in corrosion protection over galvanized steel with a powder coating. This polyurethane coating, BAC offers it as the Tri-Armor corrosion protection system. It's a thick coating that It's basically it's sprayed at the factory on top of G235 galvanized steel that's coated with the thermosetting hybrid polymer coating. And this thick coating fully adheres to the basin and completely eliminates the potential for leaks. And since it's impervious to chlorides, it really makes for an excellent alternative to 316 stainless steel. Also, if you do a web search for Tri-Armor corrosion protection system, if you just do a search online, you'll find a video that we had published that really highlights the durability of the coating in the face of many different elements, including chemical spills and explosives. So it's not just a fun video to watch, it's also informative and can show you the durability and how long a polyurethane coating can last. Now, for even greater corrosion protection, you can add a fiberglass hot water basin. That's the distribution basin that's shown at the top here. It says PFRP. You can add that to the unit. Now, this particular unit that's shown includes a polyurethane coating in the cold water basin, the thermosetting hybrid polymer powder coating on the casing panels and the structure, and the fiberglass distribution basins. This configuration is cost-effective, and it's a great alternative to stainless steel, while still providing a basin that offers greater protection than 316 stainless steel against chlorides. And also, like stainless, passivation is not required since all steel panels are coated with a protective coating. Now that I've gone through the material of construction options, let's talk about how we can save water. The two main components of water consumption in a cooling tower are evaporation and blowdown. And they're shown here on this tower graphic. Evaporation is the driver for evaporative cooling, so it's always going to occur, and it's always going to be a function of the building heat load that's sent to the tower. So the evaporation, it is what it is. It's going to occur, and it's going to happen at the same rate across all towers. Now, blowdown, on the other hand, can be controlled. And blowdown is the discharge of water from the system that maintains the desired water quality level. So by using more advanced materials of construction, like the polyurethane coating, there's a great opportunity to reduce on-site water usage. Always make sure that you consider the cooling tower manufacturer's water quality guidelines. This table that's shown here includes BAC's guidelines, which are pretty typical for the industry. Now, note that there are different guidelines for each material of construction, and remember, these are general guidelines based on empirical data and historical data. So deviating from the manufacturer's guidelines, all it's going to do is affect the cooling tower's lifespan accordingly. And as I said earlier, depending on the water quality of your system and the allowable levels of corrosion that you're willing to accept, you can choose materials that allow you to save water and reduce your total cost of ownership. So now I just wanted to summarize everything that we discussed. First, we reviewed the HVAC system design. I compared water-cooled systems to air-cooled systems and explained why water-cooled systems offer the lowest total cost of ownership. Then I went into design methods that can be used to increase energy efficiency by 50% and reduce system costs by 33%. Can also increase equipment lifespan and system reliability. And finally, I reviewed recent technologies, including more advanced heat transfer technologies, and one in particular that increases thermal performance by 30% over traditional counterflow designs, more reliable and energy efficient drives that can reduce energy by 10%, and advanced materials of construction that can increase system reliability and can extend the equipment lifespan while reducing water usage. So this concludes the webinar, the formal presentation. I want to thank all of you for your time. Really appreciate everyone watching and listening, and we look forward to answering your questions. Questions have come in that we've reviewed, and we're going to answer some of them now. For anyone that has questions that you want to ask outside of the presentation, please don't hesitate to contact us. Feel free to contact us. You have the email listed on the screen. And also, if we're not able to answer everyone's questions, we'll reach out to you and provide answers to your questions. We look forward to your feedback. We also have information about our ASHRAE booth on the screen, so please feel free to visit us at ASHRAE, and we look forward to meeting you. So with that, Steve and I are going to answer some questions.
So we have a couple questions on which is more efficient, an open tower or a closed circuit cooling tower. And I guess the general answer to that would be that open cooling towers have about twice the capacity of a closed circuit cooling tower at a given horsepower. However, when you're making those comparisons, you really need to compare the closed circuit cooling tower to an open circuit tower with a heat exchanger. So then when you're considering the installation costs and flexibility, the closed circuit cooling towers really provide an excellent option to increase reliability and ensure good performance.
Great. We actually had multiple questions asking if the water-cooled savings or the water-cooled versus air-cooled system, if those savings of water-cooled systems include maintenance costs, and the answer is yes. That chart does include first costs and maintenance costs over time. And for those of you that have specific questions or want some clarification, certainly feel free to reach out to us. We can definitely have a discussion about the savings that you're going to see using water-cooled systems.
Okay, and a question on the direct drive fan systems. So what's the price point of the direct drive fan system as compared to a conventional drive system? And the price premium really depends on the motor size and the unit capacity. So while there's maybe not a specific answer to that, it generally provides a payback of less than 4 years in energy savings and reduced maintenance costs when compared to a conventional belt or gear drive system.
There were several questions that came in again about some of the examples that we showed. Let's see, what was the kilowatt per ton used for the air-cooled system? Again, I just want to reiterate for specifics. I'd have to review that specific example, but we can reach out to those that did ask this question and have that discussion about air-cooled versus water-cooled systems. Okay, couple questions again on price points and related to material of construction. So related to galvanized versus stainless steel versus the coated tri-armor basin. So maybe a little bit difficult to give a specific number, but the stainless steel typically maybe 1.5 to 2 times the galvanized pricing. The coatings also. The coatings will typically be about the same as what you can expect for stainless steel. And the coatings really offer, and it depends on the type of coating, but particularly the polyurethane coating, just to clarify, it can really be a major advantage particularly over 304 stainless steel, and can really compete with 316 stainless in terms of its effectiveness. Another question on direct drive motors. So Ben had mentioned they're available in larger motors right now. In fact, they're available in any motor size, but what you'll find is that on the larger horsepowers, the payback is most favorable at the largest motor sizes. One more, another question is regarding some of the analyses that we showed in terms of having extreme efficiency towers, what's considered the cooling tower life to be in these analyses. So the analyses use a 20-year life of the tower. Tower life, it's one of those questions that we get fairly frequently, and typically a tower can last, I believe the average life is 17 years, and that's even per handbook as well.
If you look at the ASHRAE handbook, the HVAC applications handbook from ASHRAE, in their owner and operating cost chapter, they actually list cooling towers, galvanized steel cooling towers, with an estimated service life of 20 years. So by using alternate materials of construction like stainless or tri-armor basins, you can easily extend that way beyond 20 years. Of course, that's all dependent upon whether proper water treatment and maintenance have occurred during that lifespan.
Okay, well, we're going to wrap up. We hope we answered many of your questions. And again, we're going to reach out to you if you send a question we weren't able to answer it. Again, thank you to everyone that participated and that listened, and we look forward to seeing you at the AHR Expo.